hello everyone. So now from prime ozone to ozone. All ozone providers owe their success to this powerful molecule and its unique, extraordinary features, which we will now look into. Ozone is a similar molecule to oxygen, more specifically an allotrope of oxygen, one of the different physical forms in which the element can exist. At room temperature, both ozone and oxygen are gases, but while oxygen is odorless and colorless, ozone is characterized by a pale blue color and a unique strong odor, which gave it its name. The word ozone comes from the Greek word ozine, which means in fact to smell. Molecules form when the total energy of the electrons is lower in the molecule than in the individual atoms. The lower the energy, the more stable the molecule. The oxygen molecule, O2, is the lowest and therefore most stable energy state and most common oxygen allotrope in nature. There is a very strong double bond between the two oxygen atoms, which we need energy to break, electricity in normal practice. A small part of the electricity that we apply to oxygen will be transferred to its atoms, bringing them to a higher energy state, individual oxygen atoms, also known as oxygen radicals. Oxygen radicals are characterized by very high energy. They are very unstable and will tend to bond with whatever can bring them to a lower energy state. When a single oxygen atom creates a bond with O2, ozone will be formed, O3. Ozone's energy level is in between those of the oxygen radical, the highest, and of the oxygen molecule, the lowest. The bond between the oxygen molecule and the third oxygen atom is a single bond, which is weaker and less stable than the double bond between the oxygen atoms forming O2. Ozone is still a very high energy molecule, which means it is less stable than oxygen. Ozone won't stay ozone for a long time. It will always tend to revert to oxygen, its lower energy state. It will do so either through a chemical reaction with a different compound or spontaneously over time. The half-life in water at room temperature is only 20 minutes, which means that over this time, half of the ozone will have decomposed back to oxygen. At higher temperatures, the half-life will be shorter. In other words, in warmer water, ozone decays faster. This is not only true in water, heat in general destroys ozone, which is a critical aspect in the design of ozone generators, ozone distribution systems, and ozone processes. Temperature can play an important role in the design of ozone systems, especially for application to warmer effluents, like, for example, industrial wastewater. Temperature is also important when the reaction with the target compound itself generates a high amount of heat, which could affect the next steps in the process. When ozone reacts with certain compounds, heat is generated, and if these compounds are present in high quantities and the effluent is being recirculated for complete treatment, its higher temperature can make the application of ozone less and less effective over time. Next slide, please. Thank you. Ozone and oxygen are both essential for our survival. For example, the ozone in the atmosphere shields us from the sun's harmful UV light. But ozone, unlike oxygen, is not a gas that we should breathe. It would have a harmful effect on our lungs. This led to the common misconception of ozone being a very dangerous chemical, while in reality, ozone is not any less safe than other common substances used in the industry. One clarifying example is perhaps nitrogen. It is used in food packaging, like packed meat and vegetables, to preserve their freshness, protect their nutrients, and prevent microbial growth. Nitrogen cannot be detected by humans, and the nitrogen-enriched environment depletes oxygen. So, if the concentration of nitrogen is too high, the body becomes oxygen deprived before one can even realize what is happening. That is definitely not the case with ozone, which has such a strong smell that people can detect its presence at a concentration in ambient air, which is much, much lower than what would be dangerous. But let's look together at some ozone facts, which will hopefully make us more familiar with this substance. Ozone is naturally occurring. It is produced, for example, by lightning and by UV light from the sun. A small percentage of the Earth's atmosphere is ozone, and ozone is also part of the stratosphere. Ozone is approved as a safe biocide according to the Biocidal Products Regulation. An active substance must be evaluated and approved before what produces it can be made available on the market or used in the European Union. FDA rules establish that ozone is generally recognized as safe, and that means it can be used on food products. The safe exposure limit, what man can safely breathe for 8 hours, is a time-weighted average of 0.1 ppm. Ozone has been used for over a century to treat drinking water, and ozone is dangerous to life or health at 5 parts per million, but most humans can clearly detect ozone already at 0.02 ppm, which is 25 times lower. And finally, the number of people on hospital records that have died from ozone gas is 0. Now that we have brushed up our knowledge of ozone, let's go straight to the benefits. Coming next, the benefit of ozone on treatment processes. Because of its high energy, ozone is extremely powerful. Its oxidation potential, also known as redox potential or ORP, is a measure of the tendency of ozone to acquire electrons, to be reduced, or a measure of its tendency to oxidize, if we see it the other way around from the target compound perspective. Redox potential is measured in volts. The higher its value, the greater the species' affinity for electrons and tendency to oxidize. As we can see in this list of oxidizing reagents, ozone has the highest oxidation potential after fluorine. The use of fluorine for water treatment is, however, not practical. Therefore, ozone can be considered the most powerful oxidizer available for water treatment applications. One more thing that we can notice in the list, ozone has a 50% higher oxidation potential than chlorine gas, and more than double compared to sodium hypochlorite, which oxidation potential is often used as a reference. Another characteristic which makes ozone perfect to attack microorganisms and dissolve pollutants is its high solubility in water. Pure ozone is 13 times more soluble than oxygen, but in practice, ozone is not used pure. It is generated and applied as a gas mixture, ozone mixed in oxygen. Two parameters influencing the solubility of ozone gas in water are pressure and temperature. Higher pressure and lower temperature will lead to increased gas solubility. Lower pressure and higher temperature will lower the gas solubility. A third parameter is the percentage of ozone in the gas mixture, the ozone concentration. It can be lower or higher depending on the specific ozone generation technology that is used. But the higher the ozone concentration, the higher the solubility in water of the gas mixture. This is very important to remember when looking up values for ozone solubility. The values might be expressed at a different concentration from what will be used in a specific project. And if a project involves the addition of high quantities of ozone to an effluent, working at a higher ozone concentration can help by maximizing the solubility in water of the ozone gas. Disinfection. It is defined as a process designed specifically to destroy pathogenic organisms. It kills bacteria, protozoa, cysts, and viruses. Commonly applied disinfectants, such as chlorine, penetrate the cells by diffusion. Within the cell, chlorine affects the microorganism enzymes. UV light inactivates microorganisms by destroying parts of their DNA, leaving them unable to perform vital functions. Ozone works on a completely different principle. Because of its high oxidation potential, ozone oxidizes the bacterial cell wall. Once ozone has entered the cell, it oxidizes all essential components, enzymes, proteins, DNA, RNA. The cellular membrane is damaged by ozone, so the cell will fall apart, and the damage is permanent. What does this mean in practice? While microorganisms can become resistant to biocides like chlorine over time, they can never become resistant to ozone. Some can reactivate after inactivation with UV light. There is no such thing as reactivation of pathogens after ozonation. Ozone will be always effective. Its disinfection efficiency is independent from pH and temperature variations. Ozone can provide any level of disinfection with any quality of water and wastewater, while UV, for example, needs good transmittance to be effective. Chlorine, although suitable for the activation of bacteria and viruses, cannot be effectively used to deactivate protozoa, while ozone can. Activated carbon adsorption is not an effective method for removal of, for example, 1,4-dioxane, because this contaminant is hydrophilic, which means it has a very high affinity for water, and so it is completely soluble. Ozone can destroy contaminants even if they are completely dissolved in water. Ozone's broad effectiveness is a great benefit today, but it will be an even greater one tomorrow. Ozone is the only disinfectant which also breaks down contaminants of emerging concern. So installing an ozone disinfection system today will comply to the strict upcoming rules for removal of these contaminants. A different system will have to be replaced to comply with the same rules. Being a highly reactive oxidant, ozone has many different applications. If we just look at the so many things that ozone can do in a drinking water treatment plant, it can be used for disinfection or applied earlier in the process to reduce disinfection byproducts. It can deal with taste and odor issues, not only in surface water but also in groundwater, breaking down odor-generating compounds like hydrogen sulfide. Applied as a preoxidant, it can remove iron and manganese, and so on. There are also many possibilities to apply ozone in a wastewater treatment plant. Again, disinfection, but also color removal, odor control, COD reduction, removal of pharmaceutical residues prior to discharge to prevent the contamination of the receiving surface waters with pollutants that might affect marine life or make their way to the intake of a drinking water plant. There are ozone applications also for sludge conditioning and in the fast-growing sector of water reuse. The range of industrial applications of ozone is even wider. We have, for example, treatment of ballast water to prevent contamination of the marine environment where the ballast water is discharged with different species or contaminants loaded up elsewhere. We have cooling tower applications and applications in the oil and gas sector. Ozonated water can be used for bottle rinsing and filling, or on crops and fruits to extend their shelf life and protect them from parasites. Ozone can be used to bleach pulp and textile, but also to remove color from the wastewater of paper mills and textile factories. With these and many more applications, ozone proves itself extremely versatile, bringing benefits to a number of sectors. The benefits of ozone in the aquaculture sector are outstanding. Ozone is often used in recirculating aquaculture systems to keep the water clean and to limit the amount of makeup water needed for the fish farm operation. Using ozone for this purpose also leads to an increase in the dissolved oxygen content of the water and to a general water quality improvement, which has a positive effect on the fish health and growth. Consequentially, the productivity of the fish farm increases, not only in number, but also in each fish slaughter weight. Ozone is also used to disinfect the intake water of fish farms to prevent the spread of diseases, which could make the farm lose an entire batch of production. The positive effects of ozone can be detected even in the final product, as ozone can remove from the recirculating water compounds which might give a characteristic off flavor to the meat of farmed fish. Ozone can bring benefits to industrial processes which one would not expect. Here, we would like to share with you some of the most promising and most interesting effects of ozone in different industrial sectors. First one is surface activation. Ozone can make surfaces which would normally repel each other stick together. This is beneficial for the food packaging industry in the process step where different layers of multi-layered food packaging are glued together. Ozone will make these layers stick together quicker and increase the productivity of the food packaging production plant. We have an example of that in our closest vicinity in the city of Lund. In the process of production of solar wafers, there is a cleaning step in which heavily ozonated water can be used to get rid of chemical residuals. This step increases the efficiency of the solar wafers. Ozone has over 100 installations for this application, but it is to be noted that due to the very high dissolved ozone concentrations involved, the ozone must be produced at the highest concentrations for this to be feasible. Ozone can be used not only in water, but also in air. If ozone is injected in the exhaust of, for example, a restaurant, it can break down grease and prevent its accumulation in the exhaust ducts. This will avoid that the energy required for ventilation increases over time because of the grease buildup. And mostly important, it will eliminate a fire hazard. We have then textile bleaching. Everybody knows the effect that bleach has on clothing. What you might not know is that also ozone can obtain the stone wash effect on jeans. This can be done by special industrial washing machines made to obtain this nice design without the use of polluting chemicals. Ozone is proudly part of many of these environmentally friendly systems for jeans bleaching installed worldwide. Filamentous bulking sludge is a well-known problem at wastewater treatment plants. Filamentous bacteria grow on the sludge surface and prevent its settling. Normally, ozone wouldn't be considered a suitable solution as it is a very powerful, non-selective oxidant. So the concern would be that ozone kills all microorganisms in the sludge, including the good bacteria. Surprisingly, ozone has been proven to selectively break down the filamentous bacteria first. So a small seasonal ozone dosage can improve settling of the sludge without affecting its quality. And finally, reduction of surface tension. Ozone can reduce the energy required to pump water deep underground, a benefit, for example, in oil and gas applications.